Hello, my name is Bobby Rust, and this is a security policy presentation for Green Pace, which is part of my final project for CS-405 at Southern New Hampshire University. Security policies play a crucial role in aligning teams to ensure that code remains secure, maintainable, and scalable. One key concept in securing systems is defense in depth, a strategy that involves multiple layers of protection. The idea is that if one layer is compromised, other layers will still be in place to minimize potential damages. The layers of defense in depth include physical security, which encompasses devices like CCTV cameras, alarms, access control systems like keycards, and physical barriers like fences. These measures prevent unauthorized access to facilities and critical infrastructure. The cloud perimeter and network security layer includes firewalls, VPNs, and continuous monitoring systems, which serve as the first line of defense against external threats. Intrusion detection systems further protect against malicious activity. The host, endpoint, and application security layer includes securing servers, workstations, and mobile devices. Key practices for this layer include encryption, robust endpoint security, and the implementation of AAA, which is authentication, authorization, and accounting. Additionally, security must be integrated into the software development lifecycle to ensure that code is secure from the start. For data security, protecting data in all stages, in use, in motion, and at rest, is critical. Data in use refers to information actively being processed by an application. Data in motion pertains to information being transmitted over a network, and data at rest is stored in databases or file systems. A well-defined security policy ensures that everyone is aware of common vulnerabilities and best practices. Having a documented security policy also helps to identify areas which are not covered by the policy, helping identify gaps that can be addressed in future versions. Additionally, this policy provides procedures for requesting exceptions and establishes clear rules for policy enforcement. Standard 2 enforces the practice of validating indices before indexing an array. If no validation is done, a caller can pass values larger than the array and directly writes memory that it shouldn't have access to. For example, if you have a struct in C with two fields, the first being an array and the second being a password or otherwise sensitive data, an attacker could index past the array to get to the sensitive data because they are laid out contiguously in memory. Standard 4 is a high priority exploit because it allows direct access to executing SQL queries. SQL injections are a type of attack that utilize user inputs that get directly concatenated with SQL query strings and then executed by the code. This allows attackers to run arbitrary SQL queries. Here I have an example of vulnerable code that can be exploited to perform SQL injection. I just set up a database class to create a connection to a database and make some useful functions to execute a query. Has some private methods for helper functions. In our setup function, we drop the users table so that we can populate it fresh every time we run the program. And in the users table, we just create an auto-incremented ID, a username, and a password. We then populate this table with some dummy data. We just have 10 users with usernames and passwords. In the connect function, we create a SQL connection by getting the driver and then connecting to our MySQL server. We then connect to the test database that I have created. In our main function, we just create an instance of this class, and then we list out all the users. The program will then prompt the user to enter a username, and it will get that user's information. So we'll compile the code, and when we run it, we can see all the users are printed out. So I'll just select a user to get the information from, and you can see that we get this one user's username. But if we run the program again, we can construct a string that exploits the direct concatenation with the query to perform to get all of the user's data. First, we close the quote that was part of the query string in the code. And then we just enter or 1 equals 1, which is an expression that always returns true. So it'll select all the users from the database instead of just the ones where the username matches. And then I'll just put a comment here, which will ignore the rest of the query string that's in the code. And the query that gets executed, see our first closed quote here, and then we have or 1 equals 1, and then this was the hard-coded end quote that we replaced with this. So we put a comment there so that we don't get a syntax error. Instead of directly concatenating user inputs to SQL queries, prepared statements are a much safer alternative that prevent this type of attack. Refer to the documentation for the database ORM/ODM library you are using to see how to use prepared statements. Standard 3 is about string correctness. It prevents the use of string manipulation functions that write an arbitrary number of characters to a destination string. In some cases, the destination string may not be large enough to hold the source string, and in these cases, strcpy writes to memory that is out of range. Safer functions such as stir and copy only write end characters to the destination string, so it can be ensured that arbitrary memory is not written to. This is a lower priority exploit because while it is very important, when working in C++, we will usually be utilizing the built-in string data type that is part of the standard library, which is safe from these kinds of exploits. Standard 6 states that assertions should not be used in production code, as they can be purposely triggered by attackers, which terminates the running code and can be used for denial of service attacks. These are the 10 security principles identified by SEI CERT. Principle 1 is validate input, which ensures all user input is checked for errors, formatting, and malicious content. Be aware of all common injection attacks, such as SQL injection and buffer overflows. Always validate and sanitize user inputs to prevent vulnerabilities. Standard 2 is heed compiler warnings. Treat compiler warnings as errors and fix them whenever possible. Compiler warnings can indicate potentially unsafe code that can provide attack vectors to malicious actors. Architect and design for security policies. Integrate security policies into the architecture and design process when building software. Planning proactively ensures that the team is on the same page from the start, and implementing security as a first-class feature is better than fixing it later. Keep it simple. More than just a security principle, but a principle that will surely benefit the security of the application nonetheless. The more complexity in a code base, the more opportunity for bugs creeping into the code and inviting vulnerabilities. Default deny. Applications should be developed in a way that requires users to get explicit access as opposed to granting access to everyone and needing to revoke access. Whitelist, don't blacklist. Principle 6 is adhere to the principle of least privilege. Provide users with the minimum privileges needed to complete their tasks. This both prevents attacks and prevents them from spreading and becoming larger than they would have been. Sanitize data sent by other systems. Inspect data received closely before using it. Adopt a zero-trust architecture. Create modular systems that don't depend on the safety of each other. Each module should be safe in and of itself. If one module is breached, the next module checks data sent and identifies the erroneous data. This ties closely with the next principle. Practice defense in depth. Implement multiple layers of security. Security policies should be implemented at every level of an organization, including physical, network, and software. Use effective quality assurance techniques. Write security-focused tests for all code. Have code reviews before pushing code to production environments. Use testing practices such as unit testing, regression testing, and take advantage of security frameworks to detect potential vulnerabilities in a code base. Adopt a secure coding standard. Utilize an existing secure coding standard to avoid common vulnerabilities. These are the 10 coding standards in order of priority. Validating the values of data before using it is extremely important as it can provide access to write to arbitrary memory and potentially arbitrary code execution. Standard 2, string correctness, is similarly dangerous as strings are just arrays of characters, so the same issues that arrays have apply to strings. Standard 3, SQL injections give attackers direct access to a database. They can retrieve data, change data, and in some cases, delete data. A disaster for any software system. Relying on safe memory protection tools helps prevent memory bugs and exploits that arise from them. It also removes mental overhead from the developers so they can focus on other ways to keep the system secure. The more complex a system, the more potential vulnerabilities. As computers become more and more powerful and research evolves, algorithms may become weak over time. Some already have, so we need to continue to stay on top of it and use secure cryptographic algorithms. Insecure algorithms can expose sensitive data like user passwords. Standard 6 states to use environment variables. Leaking API keys and secrets can lead to data exposure. Standard 7. Outdated packages have vulnerabilities that can be looked up as public knowledge, so they can be more easily exploited. Standard 8. Improper handling of exceptions or lack of handling exceptions gracefully can lead to denial of service attacks. Standard 9. Systems that use drastically different sizes for data types such as integers are likely outdated or use niche architecture that is uncommonly used, so this ranks lower. Standard 10. An attacker can purposely trigger assertions, which can lead to denial of service attacks. In general, denial of service is not as bad as remote code execution and direct access to data, so these types of vulnerabilities rank lower. Encryption policies. Data at rest. Secure data that is stored in non-volatile memory, such as hard drives. Securing data at rest maintains confidentiality and integrity of data to prevent unauthorized access and tampering. It also ensures compliance with data laws in organizations operating in regulated fields. Policies to secure data at rest include using strong encryption algorithms, implementing role-based access control, and practicing the principle of least privilege by giving these roles the least number of privileges needed to perform their duties. Data in transit. Securing data that is being transmitted over a network is important because attackers can intercept network transmissions to read the data. They can also alter the data being sent before it gets to the receiver, which is known as a man-in-the-middle attack. Policies to keep data in transit secure include using HTTPS for all web communications and Secure Shell Protocol, or SSH, for remote server connections. Data in use. Data in use is data that is currently in volatile memory such as RAM. When the data is being used for computations, attackers could gain access to the process that holds the data. Follow secure coding practices as outlined in this document to enforce memory safety. Also utilize static and dynamic analysis tools to detect memory errors and bugs. AAA policies. Authentication ensures that an entity is who they claim to be. Authentication verifies that an entity that claims to be authorized actually has legitimate authorization. Weak authentication is vulnerable to breaches from an entity that appears to be authorized but isn't. When a user is logged in and makes a request, they send their authorization key, which has been previously granted to them. This key is then authenticated, and the user is granted access without needing to reauthorize. To help maintain robust authentication, enforce strict password requirements, such as length and diversity of character types, and mandate multi-factor authentication for all organization accounts. Authorization grants access to a system by verifying an entity's credentials and assigning them privileges. Entities should only be granted the least amount of privilege possible to perform their task. More robust authorization should be required to perform more sensitive tasks. This protects changes to databases as it prevents changing a table or column that you shouldn't be able to. When adding new users, they are granted only certain authorizations depending on their role. Policies to help maintain strong authorization include implementing role-based access control systems and granting the least number of privileges necessary for a role to perform their tasks. Accounting logs requests to the system, keeping track of information about the entity and its behavior. Accounting enables the analysis of activity during a security incident to prevent future attacks. It is also useful for preventing attacks as they happen by detecting them early. Accessing and changing sensitive files should be monitored closely, and incidents should be sent to the security team. To enable accounting, utilize logging software to keep track of incidents both in real time and post-incident. Store logs securely to prevent tampering. Unit testing. We will be testing the string correctness security standard. Here we have an example of updating a user's username using strcpy. The setUsername function takes in a user and a new username, then copies the contents of the new username into the user's username field. Since strcpy is used and no bounds checking is performed, usernames larger than the buffer assigned to the username field overwrite the memory following the username field, which in this case is the user's password. We have a new username variable, which we can imagine is retrieved from a user. We then call the setUsername function and test that the user's password remains unchanged. In this case, it doesn't, and this test fails. As you can see, update username unsafe fails as the password became hacked. In the safe version, we have the same code, which instead uses the safer stir and copy, which only copies the first n bytes of the source string to the destination string. The user's password remains unchanged, and this test passes. As you can see, even though we tried to hack the password, it remains unchanged. Next, we have a slightly more complicated version which uses stir copy to execute arbitrary code. In this case, I have hard-coded a function that represents dangerous code an attacker would like to run. We have a struct that has a description buffer of 16 bytes, followed by a function pointer which could represent anything. We create an instance of the data struct and set the description and the function pointer to our safe function. We then would like to update the new description. But an attacker modifies the description buffer to contain the memory address of a malicious function. When the description is set, the old function pointer is overwritten with the address of our malicious function. Next time the function is called, the malicious code is run. We use memcopy to copy the address of our exploit, which is the function we would like to run, and we copy that to the destination of the 16th byte of our new description, because the description buffer is 16 bytes and we would like to write past it into this memory. The code then tests to make sure that the function pointer of the data is the address of the save function. It's not, and this test fails. The address of our data struct is this, which is hexadecimal 14F6D8. The address of the description is the same as the address of the data struct, because the description is the first field in the struct. The function address is at 14F6E8, which is 16 bytes past D8, because we're in base 16. As you can see, in decimal, this is 16 bytes past the description for the address of the function pointer. After our exploit, the data function pointer address becomes the address of our malicious function, and the code is ran. In the safe version, we have the same exact code, except we use stir and copy, which only copies the first n bytes of the description character array. This test will pass, even though we try the same exact exploit. As you can see, the function pointer address remains unchanged from the original safe function. Here's a simpler version of unsafely setting a string's value. The non-compliant code uses stir copy. To safely set a string's value, stir and copy should be used. Automation plays a crucial role in the DevSecOps pipeline, helping to reduce errors, improve efficiency, and lower the cost of maintaining security processes. By integrating automation, we also lighten the workload of the DevSecOps team, allowing them to focus on more strategic tasks. At the planning stage, automation tools can scan vulnerability databases, identifying potential threats related to the system being developed. This helps the team stay ahead of security risks and helps to ensure compliance with industry regulations and best practices. In the build stage, static analysis tools can be embedded directly into developers' IDEs, providing real-time security feedback as they write code. This allows vulnerabilities to be caught and addressed early before they become bigger issues. To maintain consistency, it's beneficial to mandate the use of a standardized IDE and static analysis tool across the team. However, since no single tool catches every vulnerability, using a combination of security tools is the best approach. During the verification and testing phase, automated unit tests should be written and run regularly, targeting threats identified during threat modeling. These tests simulate unsafe operations and ensure the code handles them safely, aligning with established security standards like SEI cert. Finally, in production, having strong logging, detection, and response system is critical. The team should be well trained and prepared to respond swiftly to any security incidents, preventing confusion in high-pressure situations. Automated monitoring can detect anomalies and immediately alert the team so that threats are assessed and mitigated before they can escalate. By leveraging automation throughout the DevSecOps pipeline, we not only strengthen security, but also create a more efficient and scalable development process. First, let's look at the problems. Cyber threats like phishing, ransomware, and data breaches are some of the biggest risks organizations face today. These attacks can cause financial loss, damage a company's reputation, and even result in legal action. Compliance with regulations such as HIPAA for healthcare in the US and GDPR in the EU is critical. Failure to meet these legal requirements can lead to fines and lawsuits. One of the weakest links in security is human error. Many security breaches happen because employees unknowingly fall for social engineering attacks like phishing emails. Finally, if an organization doesn't have a well-defined incident response plan, recovering from a breach will be chaotic, slow, and costly. A lack of preparation can turn a small incident into a disaster. So how do we address these risks? First, organizations need a strong security policy, one that isn't just written once and forgotten, but is regularly updated to keep up with new threats. Second, employee training is essential. Employees should know how to recognize phishing attempts, follow secure practices, and respond to threats. And third, having an incident response plan in place can dramatically reduce the damage caused by an attack. If something goes wrong, a well-prepared team can act quickly to contain the problem and recover faster. Risks and benefits of acting versus waiting. Acting now requires an investment in time, money, and resources, but it significantly lowers the risk of a major security incident, which could cost far more in the long run. Preventative measures are always cheaper than dealing with a breach. Waiting, on the other hand, may seem easier in the short term. Less disruption, no immediate costs. But the longer security is ignored, the greater the risk of an attack. If a breach happens, the organization will face higher costs, reputational damage, and legal consequences, all while scrambling to fix the problem under pressure. In the end, security is not just an IT issue, it's a business issue. Organizations that invest in security today will be far better off than those that wait for disaster to strike. Even with security policies in place, many organizations still have critical gaps that leave them vulnerable to attacks. Let's talk about some of the biggest weaknesses and a real-world example of what can happen when security policies fall short. One major gap is a lack of standardized employee training. Many organizations provide security training once and assume that's enough, but over time, employees become complacent and forget best practices, making them easy targets for phishing and social engineering attacks. Regular training is essential to keep security awareness high. Another common issue is the absence of an incident response plan. When a breach occurs, every second counts. Without a clear strategy, the response will be slow and uncoordinated, increasing costs, damages, and downtime. Real-world example: LinkedIn's 2021 data breach. A perfect example of why security gaps matter is LinkedIn's 2021 data breach. In this incident, an attacker was able to scrape 92% of LinkedIn users' data, including emails, phone numbers, job titles, and geolocation data. How did this happen? The attacker simply abused LinkedIn's own API to extract sensitive information. Had LinkedIn enforced stronger API security policies, this breach could have been prevented. Addressing security gaps. Key improvements. First, employee training must be standardized and required at regular intervals. Security threats evolve constantly, and so should our defenses. Second, every organization needs a well-defined incident response plan to contain breaches quickly and minimize damages. Third, API security policies must be established to prevent unauthorized access, just like in the LinkedIn breach, where weak API security led to massive data exposure. Fourth, cloud security policies must be prioritized. As more companies move to the cloud, misconfigured settings can accidentally expose sensitive data, making proper policies critical. Finally, with AI technology advancing rapidly, employees need awareness training on deepfakes, AI-generated phishing scams, and other emerging threats. While AI-generated content is becoming more realistic, employees can still be trained to detect suspicious activity. By addressing these gaps now, organizations can stay ahead of threats and avoid becoming the next major breach headline.